Hey everyone, this is Dr. Walker. In this video, we're going to go over Gauss's law. This is video 515. So in order to introduce Gauss's law, I would like to first consider the electric flux of a point charge. So what we're going to do is we're going to have a spherical surface surrounding a point charge and figure out what is the flux through that surface. We learned in the previous video that the electric flux is equal to the surface integral of E dot dA. So in this case, if we're trying to first get rid of this dot product here, we can see that for any patch on this area on the spherical surface, we can see that the electric field is parallel to that area vector, right? Because both vectors are going outward perpendicular to the surface. So we can get rid of the dot product. That is the first thing. And then the next thing is to realize that E is constant. We can take it out of the integral. The reason we know that is because we know E is given as kq over r squared. And we know that if we have this spherical surface, it has a fixed radius r, so the field is constant along that surface. So the last thing that we need to do is integrate over this area here. Well, we're integrating over the whole surface of the sphere. The surface of a sphere is 4 pi r squared. So now we can rewrite this as kq over r squared for the E, and then the surface integral is going to be 4 pi r squared. Now we can simplify. Coulomb's constant times the charge times 4 pi. The r squareds cancel out. And if we remember that 1 over 4 pi ke is the permittivity of free space, we can rewrite this as q over the permittivity of free space. So that is the result here for the flux through a spherical surface that is surrounding a point charge. This is going to help us arrive to Gauss's law really soon. But first, let's consider, well, what if it wasn't a spherical surface that was surrounding our point charge? What if it was a surface that had some weird random shape? What would be the flux through that random surface? Hopefully you can see that the flux through it would be exactly the same, because we learned that the flux is proportional to the number of field lines penetrating the surface. All three of these surfaces here have the exact same number of field lines going through them. So what this tells us is that the flux through the surface is independent of the shape of the surface. And what we're going to do is we're going to call this arbitrarily shaped surface of our own choosing, we're going to call it a Gaussian surface. So every time we have some kind of charge distribution, whether it's a point charge or a continuous charge distribution, we're going to construct some arbitrarily shaped Gaussian surface, and we're going to figure out the flux through that surface, and we're going to pick a shape that will make it easier to solve the problem, that will take into account the symmetry of the problem. But we'll see that very soon. But one more note about this Gaussian surface: it's an imaginary mathematical surface, right? It's not an actual physical surface. It's just a construction that will help us solve problems. Although it's easy, for instance, to find a flux through a sphere, well, sometimes we're going to want some other shaped surface so that we can, again, take into account the symmetry of the problem. So now we're ready to state Gauss's law. It states that the net flux through any closed surface is proportional to the charge enclosed. So it doesn't matter if it's one point charge or many, we get the same exact result. Gauss's law is a really important result. It is one of the 4 of Maxwell's equations that describe electricity and magnetism. And we'll get to all of Maxwell's equations in time. But what's really important about this one is it allows us to solve for the electric field due to different charge distributions. It can be continuous charge distributions, or discrete charges, but as long as they have a lot of symmetry, we can use Gauss's law to solve for the electric field due to these. So it's going to be very useful. One more note here is about the sign convention. As we can see from this equation, if the charge is positive, then the flux is positive. If the charge is negative, then the flux is negative. And that goes along with what we said in a previous video. We said when the electric field was coming outward from the surface, we said that the flux was positive. And if the field was going into the surface, as it would for a negative charge, we said that the flux was negative. So that agrees with that. Let's do one problem. Your turn here. It says, which spherical Gaussian surface has the larger electric flux? We have a sphere surrounding a point charge, and then we have a sphere with twice the radius surrounding twice the charge. Go ahead and pause the video and think about it. So you may be thinking, well, they're going to have the same flux because this has a larger area, surface area, and it's somehow going to compensate for having more charge. So what you really need to think about is Gauss's law that says the flux through the surface is equal to the charge enclosed divided by epsilon naught. So the flux only depends on how much charge is enclosed. There's Q here on top, there's 2Q at the bottom. There's more charge enclosed by this surface. So surface B has more flux going through it. Remember that the shape of that surface does not matter, only the charge enclosed. So in the next video, we'll use Gauss's law in much more extensively, so we can find fields due to different charge distributions. So we're going to take it one step further in the next video.